Hi. In this chapter 6, we discuss managing bandwidth. And what we mean by managing um, bandwidth is really um, managing the flow. And let me clarify the meaning of flow by saying it is the rates of data throughout the system. So that's what we mean by managing how we manage the flow, the rates of data. In this chapter, we'll talk about three main topics. And the first one is balancing the bandwidth. We're going to talk about techniques to balance the bandwidth. Mainly, um, one of the uh, well-known uh, models is the CON uh, CON process network, and we're going to talk about some synchronous and asynchronous design issues. And once we um, identify the issues for balancing the bandwidth, we're going to talk about an important issue of the bandwidth techniques, how we can uh, implement bandwidth techniques in FPGA. And the main focus here will be really on the on-chip and off-chip memories. Okay, and we're going to talk about um, streaming data of instrument. Okay, and the final topic here, we're going to talk about scaling designs. Now, obviously, from one generation to another, we need to scale and with the scaling the design, uh, there is a significant issue with increased bandwidth and how to manage it. Okay, so let's move on. So this is overall what's the chapter talk about. Well, let's go on with our slides here. And um, um, the very first topic we're going to cover here is balancing bandwidth. And as we indicated, this is really more of how you balance the rates, how you balance the rates throughout the system. Okay. Now, some of the design issues that we need to uh, pay attention is um, we need to we need to include into our consideration performance issues that include the both the rate of computation and the power. Um, and this is really an important. What we want is we don't want basically um, idle units wasting power. Also, we need to consider real-time systems as well, and their and the constraint of fixed data rate for those real-time systems. Okay. Now, Now, so let's move on to balancing the bandwidth, and the very first topic here is the COM process. Okay. Here's an example before we start COM process, and it shows the need of how we need to balance the bandwidth. Let's suppose that we want to compute this function, which is f x y x minus 1. So obviously in this computation, I have the operation of x times y, and then I need to compute x minus y, and then I need to multiply the result of these two so that I can get f. And this is illustrated down here at this graph. So you can see here x and y, they are multiplied in this multiplication unit. And then you have x decremented by 1. So this you will get here x times y, and here x minus 1. And then here we multiply x times y times x minus 1. And this is basically what I want to compute. The one thing that we notice here in this computation um, is that for the multiplier, we assume it takes 4 time units. And for the subtractor, we assume it takes 1 time unit. And then here is the second multiplier where it takes 4 time units. Now, if we examine this design, we will see that this design will have a bottleneck. So basically, you will see that this subtractor or module B, if when he calls it the subtractor module B, will finish its work and then cannot push the data here because this unit is not ready. This unit is waiting as well for the x times y. So what happened with block B is not doing any computations at all. Okay, so block B is just waiting until module A finishes the multiplication. Then block A and block B both push the results to module C. If we illustrate this in a time scale, we see that module A, which is the multiplier, takes 4 time units. Module B, which is the subtractor, takes 1 time unit. Then module B sits idle, stalls for 3 cycles. So this is 3 cycles of idleness. And the reason is because we assume that the module C cannot start, which is right here. This is module C cannot start until the both input are ready, which is a valid assumption, and and therefore this caused module B to start 3 cycles. That's bad design. That's what we are talking about, balancing bandwidth. So basically, this type of the design does not balance the bandwidth. So this simple network is not working efficiently for us. So what do we do then? Well, here's the fix. The fix is very simple. You see this subtractor here? All what we do, we need to add a buffer of 3 slots. So basically, we are pipelining, if you will, in a buffer the result of module B. Then what happened is that I can now execute, let's say for example, I have, for example, data x0 and y0. So you will see that when data y0 and x0 are in the first stage of the multiplier in this pipeline, okay, whoops, that's not what I intended to do. So this is a pipeline design here, okay, and and uh, and you will see that here I have, let's get my color back, uh, okay. So you will see that here, if I assume that I have here a y0 and x0, so this is here I will have y0 and x0 at the first time slot. Okay, and then you have a y0 and an x, oops, sorry, x0 at the subtractor. Then in the next time slot, okay, let's use another color here. In the next time slot, we will have here is we'll have y1 x1 coming and occupying. So this will be y1 x1 and 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 x0 will be here and y0 will be here. And now you will have x1 in this module B, and then x0 will be the result of x0 will be here. But basically x0 minus 1 will be right here. Okay. Then if we have another data, right, you will have, for example, let's use a different color here. We'll have let's see if we get bright green. So now we'll have y2 and x2. So now we'll have here, we'll have y0, x0 comes here, and this is y1, x1, and this is y2, x2. And then we'll have here at the subtractor, we'll have x, this x2, and we'll have x2 here. So right here we will have x0 minus 1, x1 minus 1, and then x2 in the subtractor. And then finally, when we have the fourth data, which is here, let's say at the fourth clock, y3, x3, and this is will be here x3, okay? We will have here y3, x3, and y2, x2, and y1, x1, and y0, x0, finishing the last stage of the multiplication. And here we'll have x, x3, and here we'll have x 2 minus 1, x1 minus 1, and x0 minus 1. And now at the fifth stage of the multiplier, and let's use again a different color here. Let's say, for example, we use blue. So now we'll have y4 coming, x4 coming, okay, in a pipeline fashion, and here x4, okay. So now we'll have here, this one here will have x4, and this will have here y4, x4, and y3, x3, and y2, x2, and y1, x1, and we will have here y0 multiplied by x0, right, a result, and okay, and we will have here x3 minus 1, x2 minus 1, x1 minus 1, and x0 minus 1 coming ready. Now you can see this whole thing is working in a pipeline fashion, no stall. And this is because we have added what? This is because we have added buffer. Okay? And therefore, so we can see that our buffer or FIFO is working for us to produce high throughput network. And high throughput means we are finishing part of the instruction every cycle, okay, and then once the pipeline is full, we're going to finish instruction per cycle. That's what high throughput means. Okay, all right. Now, so one of the processes that, or one of the models used to help balance the bandwidth is a model called Kahn process. And Kahn process is very similar to the data flow graph that we studied, with the exception of the following. So let's explain first what Kahn process is. Okay, so Kahn process is, okay, it is really a bunch of processes, okay, like so, process A, process B, process error, process that. Okay, so these are a bunch of processes communicating through FIFOs, and those are our communication channel. Okay, so this is our communication channel. Okay, so processes plus communication channel is what con process network is. Okay, so now we are adding a little bit more constraint that we said they have blocking reads and non-blocking writes. So let's come back to this graph. So these are these are my processes. Okay, process A, process floating point adder result, and then between them there are these communication channels. Those are communication channels or FIFOs or buffers. Okay. Now we know that if there is no data here, then this read is being blocked. If there is no data in this communication channel, okay, then this read blocks. That's what blocking. But we always guarantee that if you have a result ready, you can always write it to the next process. Okay, so if there is no data in the communication channel, you cannot read. That's a blocking read. It stops you from doing any operation. But once you produce a result, we assume that you have infinite channel here that you can push your result. That's what it says. It you have blocking reads and non-blocking writes. So that is what a CON process network. It is basically processes with communication channels, and these communication channels they block on reads and they don't block on writes. Now, so obviously this is here a COM process. Okay, so this here is a COM process model or network. So it is really very similar to the data flow graph that we studied earlier in the course. And with the simple difference is that there is for COM process there is a firing rule, and the firing rule is simply, let's just take a different color here, is that it says that this process cannot be active unless all the inputs are ready. Okay, so if they are ready, then it can start. And whenever it produces the result, it can push the result immediately. It doesn't wait. Okay, so in an essence, if you compare a data flow graph with a con process network, you can see that some people say that a data flow graph is exclusively for discrete computation. This is for continuous. Well, okay, uh, but really the firing rules, okay, here that really uh, that that let me just add here one more quick. So as we indicated here that the count process network is continuous with no firing rules unless we are adding to it a firing rule, as we have indicated here. This is the firing rule, and they kind of block on reads. Okay, all right. So in an essence, data flow graph and count process network are very similar. Okay, so next. One of the features so of the compressors networks is that they are unidirectional. Okay, so let's get here a okay. They are unidirectional flow of data. In other words, we don't have some kind of bidirectional. So if you have a process which produces a data to another process, you don't have this kind of feedback. This is illegal or not represented or not modeled by the COM process network. Okay, so the other feature of Compress network, it assumes that the size of this channel here is unbound. It means that we always assume that the size of this channel is infinite. Of course, as designers, we know that our resources are fixed, and we typically implement those channels with RAMs, and those RAMs are fixed. So that assumption from practical point of view is tough, but we can always work around it by providing the adequate and minimum size that satisfies maximum throughput. And that's the challenge in this chapter. Okay, so we need to work with the on-chip memory and the off-chip memory to implement those processes and not make them stall on writes to satisfy the COM process network. Now, one thing here is that we can also talk about the designs from the perspective of synchronous and asynchronous. If all the pieces of the design work off the same clock, then this design is designated as synchronous. If you have different designs work of different clocks, then your design is synchronous. The bottom line here really is that when your design is synchronous, things become much simpler. The checking of firing rules becomes simpler. In fact, you can eliminate quite a bit of it, and the FIFOs can be replaced with simple chain of buffers. So the message here, synchronous design allows you to uh, use simpler implementation for those channels and buffers. Asynchronous design, on the other hand, add the complexity that you have to work on some kind of controllers or state machines to manage those inputs, outputs that are coming to the processes. You don't have really global clocks, so your design really is asynchronous. You have to work of those specialized flip-flop when you interface between different domains of clocks. So things becomes really harder for the asynchronous design. So in 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 both cases for synchronous and asynchronous design, we assume that each operation takes fixed number of cycles, which is reasonable. So, for example, we can assume that the add can take one cycle, the multiply takes 4 cycles. That's a reasonable assumption. Anyway, if we can't satisfy this assumption, we can always extend the number of cycles for the operation. Okay. um, so really, the key thing here is that when we have two processes communicating, and between them there are those buffers, we would like to use the minimum number of those buffers to maximize the throughput. That's the challenge in this chapter, okay, or one of the challenges, because we don't have, this is not an infinite resource that we can add as many buffers as we want. This is a finite resource, and we want to use the minimum number of buffers, because the con process says you can always push right? And assume that you have a space for those rights, and that's part of the assumption of the con model, which we used to optimize or to balance the bandwidth in our design. Okay, so the next thing we will discuss is on-chip and off-chip memory and streaming, and this will leave it for